All right, in the previous video, we discussed the second method for finding a solution to constraint optimization. So the second method tells us if the objective function is concave and the given constraint is a linear equation, the constraint optimization can be solved in a nice way only by the Lagrangian multiplying method, so without the aid of the second derivative test. So without consideration of the second derivative of the objective function, we can solve the problem. Okay, so here I summarized our discussion in the previous video. So if the function is concave, so the objective function is concave, and the constraint is given by a linear equation, so concave, regardless of this Lagrangian multiplier. So the Lagrangian becomes a sum of two concave functions, so it's globally concave. Okay? Then, if we find the stationary point of this Lagrangian, then at this stationary point, the Lagrangian will be maximized. Okay? Because L is concave. Okay? And then maximization of Lagrangian implies constraint maximum. So we can conclude that, so we can draw the conclusion that the stationary point x star and y star is the solution to the constraint optimization problem. So that is a desired solution we are looking for. Okay? So in order to find the solution to this optimization, the only thing we have to do, we set up the Lagrangian and finding the stationary point. Okay? So that is a pretty critical method, but at the cost of some condition. Okay, the objective function must be concave. Okay, so if we think about the practicability of the second method, then how many functions are concave? But it turns out that just a very narrow scope of function is concave. Think about a x squared times y. So function f is given by x squared times y. And this is not a concave function, and this is not a convex function either. So this function is a Cobb-Douglas function because it takes the form of x to the power a times y to the power b. Okay, but in the previous example, we saw that this Cobb-Douglas is a concave just when the sum of the two exponents is less than or equal to 1. Okay, now in this function, the sum of exponents is larger than 1, so this is not a concave. And if we go back to our computation of Hessian, that was a little bit nasty, but if a plus b is larger than 1, the Hessian matrix, so the second leading principal minor, is going to be negative, right? This one is going to be negative. But if the second Hessian is so the second leading principal minor is a negative, that is a neither positive definite or nor negative definite. So this is neither convex nor concave. Right? That means with the second method, we can find a solution to this objective function. So if the constraint optimization is given by this objective function, then we can find a solution with this second method. Okay? So now we are going to generalize the previous result. It turns out that we can relax the condition concavity on the objective function. And the idea comes from this figure, okay, this simple figure. And think about this function, all right? So this function is neither convex and nor concave, all right? In this region, the graph of the function is bent upward, so it looks concave, or it looks convex in this region. But in this region, okay, the function is now bent downward, so the function looks concave. Okay, and in this region, now the function is bent upward. Okay, so it looks bent upward like this. So it looks convex. Okay, so in general, this function is neither concave nor convex. However, this function has the same property with a concave function. So think about the standard shape of the concave function. So that looks like this. Okay. So it has a single peak, right? So concave function has a single peak like this, right? So at this point, the function has a stationary point. So where this at this point, the function has a maximum value. And although this function is not concave and not convex, it has a single peak. And at this point, the function has a stationary point, and then, the function is maximized, right? So if we think about an optimization problem, so we want to see where the function takes the largest value. And the important thing is not whether function is concave or not, whether function has a single peak or not. Okay. So if the function has a single peak, we can just find the first of the condition. So finding the stationary point of the function, and then we are able to find that coordinate, the location of the stationary point from the first of the condition itself. Okay? So now we use this idea to generalize the second method. Okay, so that gives rise to quasi-concave. The idea is the function on the left is not concave, but it shares one property with the concave function. It has a single peak. So another way to express this single peak is a upper contour set. That is the set where, so set of values, so set of axes, where the function has a larger than or equal to level k is a connected interval. So think about this function, okay? And we set level k on the vertical axis. And then examine where this function takes a larger value than this level k. All right? For given this level, when x is when x lies on this interval, this connected interval, the function assumes a larger value than this level k. Okay, if we set level k here, so if we adjust the level downward, and still with this new level, the function assumes a larger value than this level over this connected interval. Okay, so whenever function has a single peak, this upper contour set, this set is called upper contour set in mathematics. And this contour set is a connected interval. If the function has two peaks, like this one, okay, then the upper contour set is no longer connected interval. Think about this level, okay, and then where this function takes a larger value than this k, on this interval and on this interval. Okay, in the middle, the function now goes below this level, so it does not belong to the upper contour set. So the upper contour set now is disconnected. Okay, so whenever function has a single peak, upper contour set is a connected interval. Okay, so having single peak is equivalent to having a connected upper contour set. Right? So with this notion, with this idea, we can define quasi-concave. So we say function is quasi-concave if every upper contour set. So no matter what this level k, or the region where the function takes a larger value, this level is a connected interval, then we say function is quasi-concave. Okay. So whenever we have the graph of the function, we can easily tell whether the given function is quasi-concave or not, because we can just see the function has a single peak or not. This function has a single peak. At this point, the function attains the global maximum. So for every k, the region where the function takes a larger value than this k is a connected interval. With this level, does not matter, right? But this one, it looks at, so this curve has two peaks at least. So this is another quasi-concave function. If we set level k here, right, now the upper contour set is going to be disconnected like this. Okay, and then this one is also quasi-concave. Right? It has a single peak. And then its counterpart is a quasi-convex. So quasi-convex is defined by defined with a lower contour set. So now where the function assumes lower value than level k. Okay? So the one standard shape of the quasi-convex function is right here. Okay? So now we set one level on vertical axis and examine where this function takes a lower value than this level k. Okay? In this region, the function assumes a lower values, so that is a connected interval. Okay, then the function has a quasi-convex. Okay, so quasi-convexity is characterized by one single minimum. So this function has just a one minimum at this point. Okay? Then every lower contour set is a connected interval. Okay? Right, so this is a quasi-convex function. And these two are quasi-concave functions. All right. Now we can extend this notion to multivariable functions. But the only difference is, in case of a multivariable functions, the upper contour set is no longer line segment, but some region. So think about this graph of this. So the graph of this function depending on two variables. If we set level k on this three-dimensional space. So the function's value is given by the height. So we cut this surface using this some plane. Then you can easily see that the upper contour set is going to be some region like this. Okay, so on this region, the function takes a larger value than this level k. So it takes a higher height. So it takes a larger height than this point. Okay. So then how do we say multivariate function is quasi-concave or quasi-convex? Now we have to adopt this notion, convex set. Okay. So although we use the same terminology, convex, convex function and convex set have a totally different meanings. So set, we say set is convex if any 2 points u and v in the set is a line segment belongs to the set S. Okay, so remember this expression, theta u plus 1 minus theta times v. That is a parametric equation of the line segment between u and v. Okay, so convex set looks like this. Okay, so we have this set. Suppose that we have this set. Then we choose any points in the set, say C and D, and connect these 2 points with a line segment. And if this line segment still lies in the set, then we say the set is convex. Okay, so that is another example of a convex set. This is also convex because if we choose any 2 points in this shape, the line segment is still inside the set. So this is another example of a convex set. But this set is not convex. If we choose these 2 points, G and H, now the line segment, some portion of the line segment is outside of the set, right? So this is not a convex set. And one donut is one example of non-convex set. So think about this set, okay? One donut. And if we choose these 2 points, this point and this point, and U and V, and the line segment joining these 2 points, some portion of that is outside the set, so this is not a convex set. Okay, and this key also not a convex set because if we choose these 2 points, some portion is outside the set, so not a convex set. Okay, so in unidimensional space, connected interval is a convex set. So we have a just connected interval, say from A to B. Okay, we choose any 2 points inside this set. its line segment still belongs to this set. Okay, still inside the set, so it is a convex set. But this connected interval, say from here and here, then this is a not convex set in the unidimensional space, because if we choose one point here and the other point from here, let me call this U and V, and the line segment joining these 2 points, now this portion is outside the set, so the disconnected interval is not a convex set. Okay, so using this notion, we can define a quasi-concave function in multivariable cases. So function f is quasi-concave if every upper contour set of f is a convex set. Okay, and its counterpart quasi-convexity can be defined as follows. A function is quasi-convex if every lower contour set of f is a convex set. Okay. All right, so when function is given by utility function, quasi-concavity means so every upper contour set is a convex set. So if we draw a one-level curve, that was the indifference curve. So we have two commodities, good one and good two, good one and good two. And think about utility function x1 and x2. And then drawing one indifference curve by setting the level by k. Okay, that gives us one indifference curve in this commodity space. So think about the upper contour set. So the set of bundles x1 and x2 giving higher level of utility than this level k. That is going to be this region. Okay, because when consumer consumes more goods, the consumer will be better off. Okay, so we'll be happier, meaning that enjoying higher level of utility. So the upper contour set of this utility function is going to be this region. And this region is a convex set because if we choose any 2 points inside the set, say this point and this point, and its line segment joining 2 points, okay, still belongs to this upper contour set. So as the upper contour set is convex, so utility function is quasi-concave. Okay, so quasi-concave utility function is characterized by this convex upper contour set. Okay, so it has a very important implication. So if the upper contour set is convex like this, then the marginal rate of substitution, that is the slope of this indifference curve, is diminishing along the curve. So here we have a very high marginal rate of substitution because the slope of the tangent line, so slope of the tangent line to this curve is very steep. Okay, very steep. Okay? And that is a diminishing as we increase the x1. So at this point, it is almost flat. Okay, so that is a consequence of this convex upper contour set. So whenever utility function is quasi-concave, upper contour set is convex, so it has this shape. So as a result, we have a diminishing marginal rate of substitution. I want to talk about its implication further, but let me skip that. You're going to study that in the intermediate microeconomic class. All right. So instead, let me talk about some mathematical properties of quasi-concave functions. So it has a very similar to concave function. We know if function is concave, its negative is convex. Okay, and then same statement holds for quasi-concave and quasi-convex. So if function is quasi-concave, its negative becomes quasi-convex, and vice versa. So if some function is quasi-convex, then function is its negative is going to be quasi-concave. All right, and then second property is important. Concavity, so quasi-concavity is a weaker notion than concavity. I think that is quite immediate from this figure, by comparing these two. Although this function is not, concave, it is quasi-concave. Okay, so quasi-concavity is a weaker notion than concavity, in the sense that concavity, so if function is concave, then it's automatically quasi-concave. But converse is not true. Although function is quasi-concave, it is not necessarily a concave function. All right? So here is one example. Think about x squared, this quadratic function defined on positive interval. And this is a convex function. So here is the graph of x squared. So graph of x squared. Okay. So with this graph, we can easily see that this function is quasi-concave because the upper contour set, no matter what the level k, now we have a this connected interval. So every upper contour set is a connected interval, no matter what the level k is. So it is a quasi-concave function. So even though some function is convex, it may be quasi-concave. Okay? So although x squared is a not concave function, it is quasi-concave. Okay? So quasi-concave generalizes this concavity way further. All right? And then one more important property about this quasi-concave is the next. Concavity was a cardinal property. It's not preserved by monotone transformation. So the previous example was a square root of x. It's monotone transformation. So square root of x and then raised to the power 4. Then we obtain x squared. So now we lose concavity. This function is convex after taking monotone transformation. Okay? But quasi-concavity is preserved by any monotone transformation, meaning that if the function is concave, okay, then it means it's quasi-concave, right? And we take the monotone transformation, it's still quasi-concave. So not concave, but quasi-concave. So let me repeat one more time. So if f is quasi-concave and g is some increasing function, right? Then we can make sure g of f, so this composite function, is quasi-concave. If we think about why this is true, just remember the definition of quasi-concavity. So every upper contour set is a connected line. So if function is quasi-concave, we know that its upper contour set, so x, such that f of x larger than k. This is a connected interval. Okay. Now we examine g of f of x. So whether this upper contour set is a connected interval. Right? But because g is increasing, so it allows for an inverse function. Okay? So if we take the inverse of both sides, then we obtain f of x is higher than or equal to g inverse of k. Right? So that is another level. Because f is quasi-concave, for every level k, this set is a connected line, convex set. Okay? So because the upper contour set of this composite function takes this form, so set of x in the domain such that f of x is larger than or equal to some level. So let me relabel this k prime. Okay, but no matter what the level k, this upper contour set is quasi-concave, and upper contour set of the composite function takes this form. Okay, so these two are the same. So it is a quasi-concave. So this composite function is quasi-concave. All right. So quasi-concavity is preserved by any monotone transformation. All right. So here, square root of x is a concave function. So by the second property, it is quasi-concave. And if we take any monotone transformation, so raised to the power 4, now we obtain x squared. So we lose concavity, but still quasi-concavity survives. So it's still quasi-concave, okay, as we saw here. All right. And then there's another way to test quasi-concavity. So if the function is twice differentiable, we can adopt the following criterion to determine whether a function is quasi-concave or not. So that is given by bordered Hessian. So when for concavity, we use the Hessian matrix. So Hessian matrix is right here. And this matrix is called bordered Hessian in the sense that Hessian matrix is bordered by these two, so one column and one row. Okay, and this column and row consist of just a first order derivative of the function. Okay, so in that sense, this is called a bordered Hessian. So the way to test on concavity, quasi-concavity, we first compute a bordered Hessian, and then check the sign of the rth bordered leading principal minor. Okay, but in this bordered Hessian, the first leading principal minor is meaningless. That is fixed by 0. Okay, so we don't have to check the sign of 0, right? That is 0. Okay, so we examine, excuse me. So we examine the second order, the second principal minor, the sign of the second principal minor. Okay, so if the second is a negative, and the third one, so second is right here, the second principal minor is this 2 by 2 matrix. So if the determinant of this 2 by 2 is negative, so non-positive, okay, and if the last one, determinant of 3 by 3 is a non-negative, then function is quasi-concave. Okay? And if the sign of this is a strict, then f is a strictly quasi-concave. Okay, but this test is not that practical because it entails a heavy computation of so heavy computation. So in order to compute this bordered Hessian, we have to compute the first order derivative, and in addition, we have to compute the second derivative, and we have to compute this 2 by 2, determinant of this 2 by 2, and determinant of 3 by 3. Okay? So better way to see whether a given function is quasi-concave or not is using the third property. So this ordinal property. So we know if given function is quasi-concave, and then the function is some monotone transformation of the so underlying function f, then we can make sure that this monotone transformation is quasi-concave. So let me show that here. So we are given x1 squared times x2. Okay. So we want to tell whether, so we want to determine whether this is quasi-concave or not. All right. So we may adopt this methodology. So we may adopt this criterion. So by computing the bordered Hessian and check the sign of this second and third leading principal minor to see whether this function is quasi-concave or not. But the another way, much more practical way is think about this function. Okay, x1 squared times x2. That is a monotone transformation of x1 to the power 1 half. Oh, sorry, x1 to the power, x1 to the power 2/3 and x2 to the power 1/3. because if we take a monotone transformation here, so raised to the power 3, then we obtain x1 to the power squared, so x1 squared times x2. Okay, so the given function can be thought of as the monotone transformation of this. Okay, so that is a Cobb-Douglas. Okay, and we know that if the sum of exponents is less than 1 or less than or equal to 1, the function is concave. So we know this function is concave, and we take the monotone transformation. X cubed is a monotone increasing, so it's a monotone transformation. So the function, f is quasi-concave. Okay, so this Cobb-Douglas function is concave. Okay, so quasi-concave, because quasi-concave is a weaker notion than concave. So concavity implies quasi-concavity, and the given function is a monotone transformation. Monotone transformation of this Cobb-Douglas x1 2/3, x2 1/3. So monotone transformation of one quasi-concave function, so it is quasi-concave because quasi-concavity is an ordinal property that's preserved by any monotone transformation. Okay? And now think about this function. Linear function is concave and convex. Okay, so it's both quasi-convex and quasi-concave. So it is both concave and convex. So quasi-concave and quasi-convex. All right, and the last example is right here. X2 minus ln x1. So for this one, let me use this bordered Hessian. So for this function, it's not that difficult to compute this bordered Hessian. So if we have a function x2 minus ln x1, now bordered Hessian takes the form of 0, f sub 1. So the first order derivative with respect to x1 gives negative 1 over x1. Remember, the derivative of a natural logarithm is the reciprocal, and f sub 2, that is going to be 1. Okay? And this bordered Hessian has so its first row is the same as the first column, so we just copy and paste here. Okay? And then we compute the Hessian matrix. F sub 1, 1, the derivative of this guy is 1 over x1 squared. Okay? And f sub 1, 2, f sub 1 is independent of x2. So that is going to be 0. So is f sub 2, 1. By Young's theorem, we know these two are equal to each other. And f sub 2, 2, f sub 2 is a constant, so that is going to be 0. Okay? Now we compute b sub 2, the second leading principal minor. So the determinant of this 2 by 2, that is going to be negative 1 over x1 squared. Okay? So that is a negative. Negative x1 squared. That is a negative. All right. And then the last one, b sub 3. The determinant of this 3 by 3. Now we expand using this third column, okay, because it has 2 zeros. So the determinant of b3, so determinant of this b, so b3 is going to be 1 times eliminating this and this one. We have this matrix, so whose determinant is negative 1 over x1 squared. Okay, I think this is right. So this is negative. Right. So I think this example is neither quasi-convex. Oh, sorry about that. I didn't tell criterion for quasi-convexity. So this is a criterion for quasi-concavity. Okay. So function f is quasi-convex if these two principal minors are negative. So if b sub 2 and b sub 3 both are negative. Okay. So non-positive, then quasi-convex, and strictly quasi-convex. So the function becomes strictly quasi-convex if both these two, so b sub 2 and b sub 3, are strictly negative. Okay. Let me write down here. Okay, so this is a criterion for a quasi-concavity, and f is quasi-convex if b sub 2, so determinant of these two, 2 by 2, and is non-positive, and b sub 3 also non-positive. Okay, so the sign of these two are the same, non-positive, then quasi-convex. And the function becomes strictly quasi-convex, if this is strictly negative, and B3 also strictly negative. Okay. So in this example, in this last example, the second leading principal minor is negative, and the third one is also strictly negative. Okay, so this is a strictly quasi-convex. All right. So now, finally, we get to this last slide. So the second method can be summarized this. So consider constraint optimization problem. So we want to maximize given this linear constraint. Okay. And now the function is given by Quasiconcave function. Okay. Then if Lagrangian has a stationary point at this point, okay, x star, y star, and lambda star, then the first two tuple x star and y star constitutes a solution to the problem. Okay, and if the function is strictly quasi-concave, then we can establish the uniqueness. So we can say further, this is a unique solution, so unique global maximum to this constraint optimization problem. Okay. So let me finish this lecture video with this example. So once again, this is not a concave function. And then constraint is not bounded. So we can apply the first method because a constraint is a unbounded. And we can apply the previous method either because the objective function is not concave. Okay, but this is a quasi-concave function. Okay, so now using this generalized method, so applying this one, the only thing we have to do is just to set up the Lagrangian and finding the stationary point. Okay? So the argument is because x squared y is quasi-concave and the constraint is a linear, okay, then we can assure, so we can guarantee that, so we can ensure that Lagrangian is quasi-concave. Okay, so Lagrangian is quasi-concave. So that means Lagrangian has a single peak. Okay, so where this function has a stationary point, the function is a maximized. Okay, so we set up the Lagrangian. I need more space here. So L is x squared times y. That's lambda m minus x minus y. So m is some parameter. We don't have to care about this. Okay, that is a constant. We maximize this function over x and y. So taking partial derivative, finding the stationary point of this L Lagrangian, then we have 2xy minus lambda, set it equal to 0. And for y, we have x squared minus lambda, set it equal to 0. And then with respect to lambda, we have the constraint. Okay, so whenever we have Cobb-Douglas, the way to solve the system of equation is divide the first equation by the second. Okay, so combine these two and divide the first by the second, we obtain lambda will be cancelled. That is going to be 1. And 2xy over x squared boils down to 2y over x. Okay, so we know x is 2y. Okay, and then substituting this one into the last equation, we obtain 3y equals m. So y is m over 3. Okay, and x is 2y, so x becomes 2m over 3. Okay, and then that is the unique stationary point of this Lagrangian. We don't have to compute lambda because just it's enough to find the value of x and y in the stationary point of Lagrangian. So we can say these 2 points. So this point, 2m over 3 and m over 3. So x star and y star. 2m over 3 and m over 3 becomes the solution to this constraint optimization. All right, so I think I discussed so many things in this week, but this is quite important. So I think it's better to have some time to go over this method in the live lecture. So not this Friday, so not tomorrow, but next Friday, let me show you several examples. So let me discuss some these methodologies, these two methods, because these two methods are quite important, in the economic analysis. Okay, so let me do some. So let me show you some examples in the next Friday to better understand this method. Okay, so hope you find this video useful, and then we should have a great day, and I'll see you in the next video.